There is a truly strange object that has passed through our solar system, flying past the Sun in a way we have never seen before. We don't fully understand what this object is, what it's made of, or even what it was doing here. In fact, at the moment, we can't even see it anymore. And yet, for months, astronomers around the world have been watching it extremely closely. This object has been given a name, 3I Atlas, and an official classification as an interstellar comet. Despite how brief its visit may be, it has already become one of the most intensely studied objects in modern astronomy. In just 4 months, nearly 100 scientific papers have been published about 3I Atlas, with even more discussion happening outside the official scientific record. Some of the claims surrounding this object sound almost unbelievable. So rather than getting lost in speculation, let us strip away the noise and focus on what we actually know about this remarkable visitor from another star system. At this point in its journey, 3I Atlas is reaching what astronomers call perihelion, the moment when an object makes its closest approach to the Sun. This is a critical phase for any comet because it marks the period of maximum exposure to solar heat and radiation. For 3I Atlas, perihelion occurs on October 29th, when it passes within roughly 210 million kilometers of the Sun. To better understand this distance, astronomers use a unit known as the astronomical unit, or O. 1O represents the average distance between Earth and the Sun. Using this scale, the perihelion distance of 3I Atlas is about 1.4 astronomical units, placing it slightly inside the orbit of Mars. While that may seem close on a human scale, it is actually a moderate distance compared to many comets that dive far closer to the Sun. Even so, this is the point at which 3I Atlas becomes most active. As it heats up, frozen material on and beneath its surface begins to violently escape into space. This release of gas and dust dramatically increases the comet's brightness and transforms it into the glowing object astronomers observe from afar. Unfortunately, this moment of peak activity is hidden from Earth's view. From our perspective, the comet passes directly behind the Sun, and the intense solar glare completely blocks our line of sight. While this limits direct observation, scientists can still study the comet before and after perihelion, allowing them to analyze how the Sun's influence alters its structure and composition. The dramatic changes observed in 3I Atlas during its approach to the Sun are driven by a physical process known as sublimation. In the vacuum of space, solid materials do not melt into liquid the way they do on Earth. Instead, they transition directly from a solid into a gas. This process occurs when frozen compounds are heated by sunlight. As gas escapes from the surface of a comet, it drags fine dust particles along with it. Together, this material forms a glowing cloud that surrounds the solid core of the comet. This cloud is called the coma, and it is responsible for much of a comet's visible brightness. The solid center, known as the nucleus, often remains hidden within this expanding veil of gas and dust. The comet's tail forms due to the influence of the solar wind, a continuous stream of charged particles flowing outward from the Sun. This wind pushes the lighter gas and dust away from the comet, stretching it into a tail that always points away from the Sun, regardless of the comet's direction of travel. The interaction between gravity, radiation, and solar wind creates a constantly shifting and elegant structure. In the case of 3I Atlas, this process is especially important because its composition is unusual. The materials sublimating from its surface behave differently than those in typical solar system comets, altering how and when its coma and tail form. These differences give scientists a rare opportunity to study how cometary activity may vary in other star systems, revealing how diverse planetary environments can be across the galaxy. The story of 3I ATLAS begins with its official discovery on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System, or ATLAS. This system consists of multiple telescopes located around the world, continuously scanning the sky for objects that move against the background of stars. Initially, 3I ATLAS appeared to be just another newly discovered asteroid. However, astronomers quickly noticed something extraordinary: its speed. All objects in the solar system orbit the Sun due to gravity, and their speeds are determined by how tightly they are bound to it. Earth travels around the Sun at about 30 kilometers per second, while Mercury, much closer to the Sun, moves at roughly 48 kilometers per second. The first ATLAS, by contrast, was measured traveling at 58 kilometers per second while still far from the Sun, near the orbit of Jupiter. This velocity was far too high for an object gravitationally bound to the solar system. Instead, it indicated that the object was on a hyperbolic trajectory, meaning it was simply passing through. This discovery immediately confirmed that 3I ATLAS originated outside the solar system. It was not captured by the Sun's gravity and would not remain here. After completing its brief encounter, it would continue onward into interstellar space, carrying with it a record of conditions from a completely different star system. The designation 3I reveals that this object is only the third interstellar visitor ever detected in our solar system. The first, Oumuamua, was highly unusual and showed no clear signs of cometary activity. The second, 2I Borisov, behaved almost exactly like a typical comet, despite its interstellar origin. 3I ATLAS differs from both in several key ways. The most obvious difference is size. While Oumuamua measured only a few hundred meters across and Borisov reached about 1 kilometer, 3I ATLAS may be as large as 5.6 kilometers in diameter. This makes it the largest interstellar object ever observed. Speed is another major distinction. The first ATLAS is moving significantly faster than either of its predecessors, suggesting it was ejected from its home system with tremendous force. But perhaps the most intriguing difference lies in its direction of approach. Unlike previous interstellar visitors, which approached from roughly the direction the solar system is moving through the galaxy, 3I ATLAS entered from the side. Its trajectory is aligned within just 3 degrees of the plane of the ecliptic, the flat disk in which the planets orbit. Given the vastness of space and the infinite directions from which an object could arrive, this alignment is an extraordinary coincidence. Determining where 3I ATLAS came from is a complex challenge, but astronomers have been able to narrow it down. Its incoming path points toward the galactic core, the densely populated center of the Milky Way. However, understanding its true origin requires viewing the galaxy from the side. Most stars in the Milky Way lie in a thin disk, but above and below this region exists a less crowded structure known as the thick disk. This area contains older stars and experiences fewer violent events, such as supernovae and close stellar encounters. Objects here can remain undisturbed for billions of years. Scientists believe 3I ATLAS likely formed in this thick disk. Based on its motion and chemical properties, it may be as old as 7.6 billion years, making it nearly twice the age of Earth. By retracing its path backward for 10 million years, astronomers identified 93 stars it may have passed near. Remarkably, even its closest encounter was still about 0.3 light-years away, highlighting how isolated its journey through space has been. Compared to those vast distances, its current passage just 1.4 astronomical units from our Sun is an incredibly rare and close encounter on a cosmic scale. Even before its official discovery, 3I ATLAS was unintentionally observed by NASA's TESS spacecraft in May 2025. During this time, scientists noticed that its brightness increased far more rapidly than expected. Instead of a modest rise, its brightness increased by a factor of 5. This dramatic change confirmed that the object was not an asteroid, but an active comet. However, its chemical composition was highly unusual. Observations revealed that its coma was dominated by carbon dioxide, with a CO2-water ratio of approximately 8:1, the opposite of what is typically observed in solar system comets. Carbon dioxide ice sublimates at much lower temperatures than water ice, explaining why 3I Atlas became active far beyond Jupiter's orbit. Later, as it approached the Sun, water vapor suddenly appeared in massive quantities, exceeding expectations for a comet at that distance. Even more puzzling was the detection of nickel without iron, an unusual imbalance given that both metals usually form together in stars. Only later did iron begin to appear, eventually restoring a more typical ratio. These strange chemical transitions suggest that 3I Atlas is revealing processes rarely seen in our own solar system. One of the most valuable observation opportunities occurred on October 3rd, when 3I Atlas passed within 0.19 astronomical units of Mars. Thanks to the numerous spacecraft orbiting and operating on the Martian surface, scientists were able to capture rare images of the interstellar comet from a unique perspective. Although these images lack fine detail, they represent the closest observations of an interstellar comet ever made. Further observations may come from NASA's Juno spacecraft when the object passes within 0.36 astronomical units of Jupiter on March 16, 2026. By that time, 3I Atlas will be cooling down and becoming less active as it exits the solar system. Whether its strange characteristics were shaped at birth or accumulated over billions of years of travel remains unknown. What is certain is that this brief visitor has provided scientists with an unprecedented glimpse into the diversity of objects that wander between the stars.